x equals y minus 5 squared is actually correct. That is the equation of the inverse. The problem is that they're going to give it to you in y equals format, right? They're usually not going to give it to you in x equals format. So the first step is to change your x and y's, because that's what you do when you have an inverse, your x and y switch. But the second step is to solve for y, because if you want to see what it looks like, you're going to have it in y equals. If you want to punch in your calculator and look at it. And also, if it's a multiple choice answer, they're not going to have it in that form. That is the actual equation. It is correct, but that's not the form you're going to see. So we have to keep going. So we want to get y by itself. So how could we get y by itself? What's the first thing we'd have to do in this case? Square root it. And when you take the square root, what do you always have to remember to take? The positive and the negative. So when you take the square root, you're going to take the plus and the minus. And then that's going to cancel. And so you're going to have y minus 5 equals plus or minus square root x. And then you're going to add your 5 over. So you get y equals 5 plus or minus square root x. Now, you'll catch yourself, because if you put the original into your calculator, the original is a quadratic, right? So it has two arms like this. If you forget the plus or minus sign, you're only going to get one arm sideways like this. And you'll be like, wait a second, that's not the inverse, because it's only half the graph, right? So then you'd be like, how do I get the other half? Oh, right, when I take the square root, I have to take the positive and negative, because that's how you get both arms. So let's punch it into our calculator. So type in your original one, this one here, into your y1. I'm really going to get my calculator downloaded again. So type that into your y1. Y equals x minus 5 squared. Now, are those of you who know how to make the lines thicker and thinner so you can look at both your graphs and know which one's which? Okay, so into your y equals your first one, I'm just going to leave it like that. I'm going to go x minus 5 squared. Does everyone know how to type that into their calculator? I hope so. Okay, in y2 and y3, you're actually going to have to put these in separately, because there's no plus or minus button. So you'll have to go 5 plus square root x in one of them, and then 5 minus square root x in the other. And remember, when you put them into your calculator, you have to put them in the way you say them. So if you say 5 minus square root x, you have to actually put 5 minus square root x. Don't go 5 negative square root x. It will give you something totally different. You have to punch it into your calculator the way you say it. So if it was like x plus a negative 3, then you'd have to go x plus a negative 3. But if it was like x minus 3, then you use the minus sign. You have to type them in the way you say them. Some people put negatives in for subtractions, and that gives you totally different graphs. So in your first y1, you're going to have y equals x minus 5 squared. In y2 and y3, you're going to have 5 plus square root x and 5 minus square root x. Does everyone have that? Yeah? So if you don't have the fancy colored ones that give you two different colors, you can actually make one of them be a thin graph and one be a thick graph. I always let my first graph be the thin graph, so I just leave it how it is. And then I make my second graph be the thick graph, so that I know that y2 is represented by the thick graph always. In this case, it's going to be y2 and y3, because they're one graph. So what you do is you go to y2, and you'll have to do this to y3 as well, because they happen to be the same graph. You go to y2, and you arrow all the way to the left, to being on that slashed line. Okay? So arrow all the way till you're on that slashed line, and hit enter once. Now press graph. So it'll draw it thicker, right? Which in this way, you know the first one's a parabola, so you could figure out the second one is. But sometimes you have two graphs on, just transformed and moved. And it's nice to know, hey, y2 is actually the thicker line if you don't have the colored graphs. So you can really only do that. So then you'd have to do it to your y3 as well to make it thicker, so that they actually both are thicker. Because y2 and y3 happen to be one graph. Okay? But if you have the colored ones, you're golden. You have this way before everyone else anyway. So if we sketch our original on here, you guys have to sketch it on the graph, okay? So we're going to sketch our original. It's going to be starting at positive 5 and 0 is going to be my vertex. And the reason why I know that is that h and k gets my vertex, and my vertex is at 0. So it's going to be 5 and 0. Remember when it was in that form with the squared? That gave you your vertex. That's how I know it's at 5 and 0. So you're going to get here and here, and you're going to get it. Should look like that. Because the parabola hasn't been stretched at all, right? And your normal parabola is 0, 0, 1, 1, negative 1, 1. This one hasn't been stretched at all either. It's just been translated. So if you took your original, which is 0, 0, 1, 1, negative 1, 1, and we just shifted that whole entire graph to the right 5, we'd get the new graph, right? We can use our transformations as well in order to draw new graphs. You don't need your calculator. So this would be the original. Now what I want you to do is draw the line y equals x. The line y equals x is really easy to draw because if you have a line y equals x, which is the inverse line, it's the identity line, it's what it's called. It's the line that the inverse reflects on. It's really easy because whatever y is equal to x is equal to, right? So 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, negative 1, negative 1, negative 2, negative 2. So the line y equals x is really easy to draw. So you'd have here. And I'm going to draw it dashed. And not very well, it seems. Okay? So that's going to be the line that my graph reflects on. Remember when it reflected on the x-axis and only at the x-axis, the invariant points were on the x-axis? And when it reflected on the y-axis and only on the y-axis, no other crazy things were happening, the invariant points were on the y-axis? Inverse graphs have invariant points along the line y equals x because that's what it's going to reflect on. So this graph, the inverse graph and this graph are going to have two invariant points, one here and one here. So if you want to find out how many invariant points there are on an inverse graph, you just literally draw the line y equals x through it and count how many times it crosses. Most people are really good if it's like 3, 3, they're like it's invariant because 3, 3 is going to stay 3, 3, right? But they'll never pick out the ones that are like decimals, like this one here. They're like, oh, I don't know. But if you just always draw the line y equals x through either your original or your inverse, you'll know how many invariant points there are because it's going to reflect on them. So if I draw my inverse graph, I can just take these points and I can sketch them flipped, right? I don't need my calculator. I don't even need that equation. So this one's at 5 and 0. So the inverse point is going to be at, so if f of x is at 5, 0, f negative 1x is going to be at 0, 5. Do you see how those points are completely reflected across this line? Then I have 4 and 1. It's going to become 1 and 4. So that's perfectly reflected on this, about this green line. 6 and 1. It's going to become 1 and 6. So that's completely reflected along it, same distance. And then this one is 7 and 4. So it's going to become 4 and 7. So they're actual mirror images about that green line. Do you see that? Now, mark the invariant points. Well, they're going to be here and here. Do I need to draw the inverse graph to actually mark my invariant points? No, I can draw my original graph, draw the line y equals x, and wherever it crosses the original, that's what points are going to stay. Okay? Now, this is the ultimate question that comes up a lot. So let's just say the domain. The domain of the original, this is the original. The domain of the original is XER, right? So what does that tell me about the inverse? What does that tell me about the inverse? The range is going to be YER. Now, I can tell based on this that the range is actually going to be YER because I drew the graph, but had I not drawn the graph, I would actually still know that. So f negative 1x, the range is YER. And the range of the original, the lowest y it is 0 or greater. I'm just going to show this to you as an interval. You would never write the domain as set notation and then the range is interval. I'm just showing you the difference just so we keep practicing different ways. So this is a set notation. If they ask you for set notation, this is set notation. Set notation is the set of. That's what those little squiggly brackets mean. Everything means something. These mean the set of x values such that, that's a little straight line, means such that x is an element of the reals. And then this is that set, okay? So that's set notation. Interval notation is the brackets, the round and square brackets. So if they ask you for interval notation, that's that one. Okay? That's what interval it's between. So this one is greater than or equal to 0, right? So I'm going to go equal to 0 and greater than. Interval notation for the most part is easier, except for when you have pieces, like when you have like rational functions where it's this piece and this piece. Some people find or set notation better. So if the range is 0 to theta, this is why interval notation is easier. The domain of the inverse is 0 to theta. It doesn't change because we don't actually state x's and y's in interval notation, right? So a lot of people, if they have a choice, are going to go with set interval notation because they literally just rewrite each other's in different spots. The question that gets asked all the time, the blue graph is a parabola, right? It's a parabolic function. It's a parabolic function. It's a function. It passes the vertical line test. For every x, there's only one y, right? So if I drew vertical lines through it, it passes the vertical line test, right? Now, is the inverse a function? No, if I drew vertical lines, it wouldn't pass it. How could I check if the inverse is a function without drawing the inverse? How could I check if the inverse is a function without drawing the inverse? Instead of checking for the vertical line test, I should check for the horizontal, because the horizontal would actually be the what of the inverse? The vertical. So if I drew a horizontal line through this graph here, like the blue one, okay, say I drew it here, does it pass the horizontal line test? No. So will this red one pass the vertical line test? No, because an inverse vertical line, or the original, if it was a horizontal line, would actually be a vertical line of the inverse. So what you can tell yourself is, if the original graph does not pass the horizontal line test, then its inverse will not pass the vertical line test. And will not be a function. So on a test, what they'll ask you is they'll say, and we always restrict the original domain. We will never restrict the inverse domain or the inverse range. We will always restrict the original domain. So what they'll say is, the inverse is not a function. Okay, and in this case, it's not. The inverse is not a function. What could you restrict your original graph's domain to so that when you drew the inverse, it would be a function? So what could you restrict your original domain so that when you drew your inverse, it would be a function? What is the issue? Well, when we draw horizontal lines along here, it actually is going to cross twice everywhere, is it not? But if I cut off one of those arms on the parabola, say I drop this a half of the arm, would it pass the horizontal line test? Yeah. If I dropped off this half of the arm, would it pass the horizontal line test? Yeah. If I dropped off actually this half of the arm and this bottom of the parabola and only had just this piece of the parabola left, just this little bit of the arm, would it still pass the horizontal line test? Yeah. So the most domain you could restrict this one to would be either x is less than or equal to 5, or you could say x is greater than or equal to 5. If you restricted your domain to either of those functions, the inverse would be a function, right? Could I restrict them by saying x has to be greater than or equal to 7? Would that still work? Yes. Does it encompass the most area that I could keep? No. But would it still be correct if they had that as a multiple choice answer? Yes. If they had they had that I restrict the domain to being x is less than or equal to 7, would that work? Less than or equal to 7. No, because less than or equal to 7 would actually be here. I'm not going to use green because I already used green. It would be here and then this. And would that part of the graph pass the horizontal line test? No. Okay, so you could give me the domain as x is less than or equal to 5. You could give me the domain as x is greater than or equal to 5, or any variance of that this way, right? To the right and to the left. So I could say x is less than or equal to -10, and that would still work because -10 would be a graph way up here and it would pass the horizontal line test, right? Or I could say x is greater than or equal to 6.8. It's craziness, but I could do that and it would still pass, right? So these are you would never give both of these, you just say one. You'd say, okay, I'm going to restrict the domain to x is less than or equal to 5, or I'm going to restrict the domain to x is greater than or equal to 5. But on a multiple choice answer, I could give you any variance of anything greater than or equal to 5, and it would be correct. Or anything less than or equal to 5, and it would be correct. Does that make sense? They always restrict the domain to make the inverse be a function. They never, ever restrict the inverse to make it a function. Make sense? They will never do that. So you're always going to restrict the original parabola, or whatever shape it is, to make your inverse be a function. Okay? You will always restrict your original. Which of the following 4 options of points would be invariant on an inverse graph? Which of the following 4 points would be invariant on an inverse graph? You tell me, stop me when I hit 1. 2, 9. 3 and -3. 4 and -3. Or -4 and -4. Which of those 4 would be invariant? The last one would be the only one. Because in order for it to be invariant, the point has to stay the same. So I remember saying, I think -3 and 3, and some people almost fell for that. But if I take -3 and 3, and I switch the x's and y's, is it going to be the same point? No. The only way you get an invariant point on an inverse graph is if your x and y's are the exact same. Because ultimately, what are we doing when we're finding the inverse graph? We're just flipping the x's and y's and redrawing them. Flipping the x's and y's and redrawing them, right? So 1.3 and 1.3 would be an invariant point because when I flip them, they would stay the same. So it doesn't have to be a whole number. Everyone tries to think that it has to be like 4 and 2 or 4 and 4. Then that would work. But if I give you 2.2 and 2.2, they're like, nope, decimals can't happen. If I give it to you like that and I speak it to you, most of you will be like, yeah, okay, that's true. But you'll never pick them off a graph. So let me show you something. So if I give you this graph here, okay, it's going to keep going like this. And I ask you how many invariant points are on this graph. If I ask you how many invariant points are on this graph. Actually, I won't say on this. How many invariant points are on f of x and f negative 1x? First off, do I have to draw f negative 1x in order to answer that question? That should be capital. Ooh, capital. I don't need to draw it. What's the only thing I have to draw? y equals x. If I draw y equals x and count how many, you know how many. If they want to know accurately what points they are, then they would have to end up on landing on like a cross section. They can't like accurately ask you what the points are if it's like 1.2 and like 1.2 or something, right? You'd be guessing. So in that case, if they don't cross perfectly through, all of them cross through y equals x, then they'll just ask you for how many. And it's usually a question. So what I have people do is they'll try and find out what points on this graph are like the same x and y values. Don't do that. Don't do that because you'll miss the decimal ones, right? You won't spot the decimal ones. So just draw your y equals x line. The question is this getting closer to the line y equals x? Did it get closer? It technically is. So is it going to cross somewhere? Yes. They're not that nasty on the diploma. They're not going to give you something like this where you'll be like, is it getting closer? Is it not? They'll give you the full graph and you'll physically draw the line and you'll be able to count them. Okay? So this one would have 2. Do I care what they are? No. Numeric response, but 2, move on. This is like I said to you, they've given questions where I've given questions where you were given the graph, and then I ask you how many invariant points there are so say I give you this graph. Okay? And I ask you, blank, 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 how many invariant points there are on f of negative x? F of negative x. That's a reflection in the y. How many are on the y? 1. Fill that in the first numeric response box. And then negative f of x. That's a reflection in the x. How many are there? Fill that into the second numeric response box. And then x equals f of y, or f negative 1x. You can ask it either way, right? How many would there be? Well, I'd have to accurately be the scale. Right now there isn't one, but let's pretend that this is the accurate scale. So I would draw my y equals x. And how many would there be? 1, 2, 3. And so my numeric response would be 1, 3, 3. But if you don't know how to answer one of these, you don't get part marks. You don't get it right. Okay, so you need to remember things like this. Okay, and then they could do a fourth blank, but I don't know what they'd want to do. So there's that. So we'll sketch the inverse. How do I sketch the inverse? I just do what? Take every point and flip them. X and Y's. So this one's at 1, 2, 3, 4, 5, 6. So negative 6, 0. So it's going to become 0 and negative 6. Then I have negative 4 and 1, 2, 3, 4, 5, 6. So that's going to become 6 and negative 4. And then I'm going to connect them. These are the ones that if you don't connect the points as you go along, you might get a crazy looking graph because you just connect random points again. And then I have negative 1 and 6. So it's going to become 6 and negative 1. Now, why is this one horizontal here? What do you remember about inverse graphs? Well, why is that one vertical? Sorry. Because the original was horizontal. Remember, anything that's horizontal becomes vertical. Anything that's vertical becomes horizontal. So this one's vertical here because this was horizontal in the original. 1, 2, 3, 4, and negative 3. It's going to become negative 3 and 4. And then 1, 2, 3, 4, 5, 6, 7, and 0 is going to become 0 and 7. How many invariant points? 1. Do I care what it is? No. Where these two cross would be invariant. But then some people will say, well, this one's invariant then too, right here. And then this one's invariant because they cross. Is invariant where they cross and intersect? Is that the definition? No, it's where the points do not change from beginning to end. They wouldn't change. And this point here wouldn't change because whatever decimal it is, it's the same for both. And then you swap and be the same. There wouldn't be any mapping. Well, the mapping would just be that x, y becomes x, yeah. Yeah, if you did mapping, it would literally just be that x, y becomes y, x. Yeah. Honestly, inverses aren't the worst and hardest things in the world, but people make them out to be harder, or they think they're so easy that they don't do the homework for them, and then it becomes harder. Because there's little tricks to it, right? Like how many inverse points there are, what would be the restricted domain to make it be a function. And there's all these little tiny things to it where everyone's like, ah, just switch x and y's and I'm good, which is a very small part of it. Now, some people see this. It's y equals square root x minus 2. And some people are like, it's a square root, and then they put a plus or minus sign in front of it. No. There's only a plus or minus sign when you physically take the square root. So when there's an x squared and you square root, physically, you are drawing the square root, then you put a plus or minus sign in front of it. Okay? But if the square root is drawn for you, it's whatever sign they have. And what sign is with this if there's no sign in front of it? Positive. That's it. Don't put plus or minus sign in front of it, which I find people doing because they're like, right, square root, plus or minus. It's only plus or minus sign in front when you physically get rid of the squared. Does that make sense? And you take the square root like we did when it was x squared. Okay? So let's sketch this graph. Now, let's sketch this graph with transformations. This is a radical graph. A radical graph starts at 0, 0, then it goes 1, 1, then it goes 4 and 2, then it goes 9 and 3 because you're taking the square root of all the x values to get your y's. So the original y equals square root x graph would be 0, 0, 1, 1, 4, 2, 5, 6, 7, 8, 9, and 3. That would be the original. Okay? Let's use the transformations that this graph gives us to move this one to get that actual graph. The actual graph is x minus square root of x minus 2. X minus 2 means we actually have a horizontal translation what? To right. Do our y's change? No. The whole graph just shifts 2 to the right. So 0, 0 would become 2, 0. 1, 1 would become 3, 1. This one would move 2 to the right. This one would move, oops, to the right technically. So did I actually need my calculator? No. And we do radical graphs towards the end of the semester just because we put radicals and rationals together with other functions. So the blue is actually this y equals square root x minus 2 graph, right? Now I can sketch the x equals f of y. I just take those blue points and I switch them. And I'll make it red. So this one's 2 and 0, so it's going to be at 0, 2. This one's at 3 and 1, so it's going to be at 1 and 3. And I'm going to connect them. And then look, they would be equidistant. If I drew this as my y equals x graph, look, they're equal distance from that reflection, right? So you're doing good. Then we have 1, 2, 3, 4, 5, 6, and 2. So we're going to be at 2 and 6. And then I'm going to just sketch it out. Is the inverse a function? Yes. Did I need to draw it to figure out if it was a function? No. What could I have done to the original to test if my inverse was a function? Horizontal line tests. I drew horizontal line tests through the whole entire blue graph. So I'm going to draw horizontal line tests through the whole entire blue graph. Does it cross more than once? No. So then the inverse is a function. If I draw vertical lines through my original, what am I testing? If the original is a function, right? So verticals through the original tells you if the original is a function. Horizontal through the original tells you if the inverse is a function. Make sense? We went through this on that other graph. So this is the assignment, but I'm just going to look it up just to make sure. Thank you. Make sure I want you to do that many. This is what I want to change. Instead of doing 6, I want you to do all of 5. Because what I find people are weak at, you know, there's like certain sections that I find out people like find a little struggle, like the graph to the equation. What I find people are a little bit struggling with is they forget about the rules of the horizontal and all that. The main becomes range, range becomes main. But what the biggest struggle is actually coming up with the equation of the inverse. Some people cannot solve for the y properly. Some of them are a little tricky. Okay, so I want you to do number 5. Number 5 is like you're solving, you given an equation and you have to find the inverse. So it's good practice for those ones. Don't worry about 7. I'll cross that out. 9, I want you to do A, and I want you to do D, not B. Don't worry about 11. Twelve is a really good one because those are the tricky ones. Finding the equation. Don't worry about 13. I don't want you to do 15, but I do want you to do 14. 14 is one of those where you have to restrict the domain to make your inverse be a function, and you will get one of those. And it comes up a lot in diplomas, and it for sure will come up in our tests.